This video is about using inverse functions. So before we jump into inverse functions, let's talk about what an inverse is in context of this relation. So we learned about relations before we learned about functions. It's just any pairing of x and y values would be a relation. So my first relation here has a list of 5 coordinates, a list of 5 points. If I were to graph these 5 points, I have the point 0, 6, 0.14, 0.22, 3, 0, and 4, negative 2. They happen to make a line, a straight line, but a relation does not have to have any kind of a pattern. I just happen to pick these numbers, but you don't need to connect them or anything. The relation just consists of those 5 points. I'm using this to illustrate what makes an inverse of that relation. Would be if I took all of my x and y pairs and I switched them or inverted them. If I put x in place of y and y in place of x, my new list of 5 points is the inverse of the original relation. So instead of 0, 6, I have the point 6, 0. Instead of 1, 4, I have the point 4, 1. I still have the point 2, 2. My first point was f5. Let's move that over to 6. Just counting that again. I still have the point 2, 2, then I have the point 0, 3, and I have the point negative 2, 4. So my red dots represent the original, my blue dots represent the inverse relation, and as you can see, what's happened is all of the x and y's have switched place. Let's talk about this in terms of a function. The original function is 2x minus 1. The inverse of that function is x plus 1 divided by 2. Let's see what that would look like on the graph. Then I'll show you how you can get these inverse functions by hand if you're asked to find an inverse yourself. So if the original function is f of x, I know that that's a linear function, 2x minus 1. I can graph it using any number of methods. I know the point negative 1 is there on the x-axis. I have a series of other points to connect the dots and make the line. That's my original function f of x. I'll label it f of x on the graph. The inverse function, if I simplify this so I can see what the slope is, the y-intercept, or you can plug in any number of points, it's going to look something like this. And there's my function, inverse of x. The negative 1 notation in front of the parentheses x, okay, when you're talking about functions, is not an operation. It doesn't actually mean a negative exponent. It's just a notation that means inverse function. So if you ever see the negative 1 with the f like that, it's the inverse function of the function f of x. So f of x and then f to the negative 1 of x. It's just a notation that means inverse. So on the graph, you can see the red line is my original function, my blue line is the inverse function. And the rule of thumb for these graphs, or for any inverse graph, okay, is that the inverse function is a reflection of the original function over the line y equals x. Because what's happening is all of your x's are switching place with all of your y's. So the blue line is a reflection of the red line over the line y equals x. Well, if you picture where the line y equals x is, it's kind of like this other axis. Right? It's not the x-axis, not the y-axis that you're reflecting over. It's this 45-degree angle axis that goes right up the center of quadrants 1 and 3. So inverse is a reflection over the line y equals x. Functions f and g, so if you have two different functions, f and g, are considered to be inverses of each other, provided that when you do the composition of them, like f of g of x, you simplify it down and you get just x. Or when you do the composition g of f of x, and you simplify it down, you get just x. Okay, both have to be true in order to prove that two functions are inverses of each other. So if your instructions ask you to verify algebraically that two functions are inverses of each other, that means without graphing, without looking at the graph of either one of these functions, can we prove that they are inverses of each other? And we're going to do that using composition of functions. So I'm going to start by finding f of the inverse of x, right? F of the inverse of f of x. Oh, I think I have an extra parentheses in there. Get rid of that. So f of the inverse of f of x means I'm going to take this function plug it into the f function and then simplify it down. So I'm going to get 3 times all of this minus 5. Simplify it down. When I distribute the 3 through here, it ends up just being x plus 5. And then I have this minus 5 outside of parentheses. And sure enough, it simplifies down to equaling just x. But then you have to verify that the other composition works as well. We have to find, I'll switch colors for this, the inverse of f of x. So now we're going to plug the original function, which is this whole thing, into here and prove that it also simplifies down to x. So I'm going to start with my 1/3. In place of x, put the entire other function, and simplify. This ends up being x minus 5/3, right, when you distribute it, plus 5/3. And so sure enough, it simplifies down to just x. If the original composition and this composition both simplify to x, then you know and you've verified that the two functions are inverses of each other. So what if you're asked to find an inverse from scratch? All I'm giving you here is the original function f of x, and I'm asking you to find the equation of the inverse. So the steps can be pretty simple to follow. I'm going to start by rewriting this in terms of y and x. It's just a little easier to work with y and x. And then we know that an inverse means all the x's and y's are switching places. We're reflecting it over the line y equals x. X's and y's are switching places. I am physically going to switch the place of x and y. And that's actually my inverse function. But it's not written in the right order right now. I don't like to have a function written in this order with x by itself. And so I'm going to go ahead and get y by itself in this function, so it's written in the right format. So I'm going to get y by itself. It'll be x plus 5 equals 3y. And then divide by 3, so it'll be x plus 5 divided by 3. And now it's written in function format. It's got the y by itself. So we're just going to write our final answer in inverse function notation. Remember that means f negative 1x equals, and here it is right here, x plus 5/3. You want to write your final answer in inverse function. If the original function was f of x, written like in function notation, you want to write your inverse as f negative 1 of x to differentiate between the two. Find the inverse of a power function. So what if I have a function that's not a straight line? This one would be quadratic. Well, now I have specified here that x is greater than or equal to 0 for a reason. If I switch x and y, make this x equals y squared, in order to get that to be in function notation, I need to square root it. But as you know, a square root has a plus or minus. So it's specifically telling you not to do both positive and negative square root. They're telling you that the domain of the original function is just x values greater than or equal to 0. So therefore, when I do my square root, I'm only going to take the positive square root. If it says less than or equal to 0, then you're only going to take the negative square root. So in this case, I'm taking the positive square root of both sides. And so the square root of x, without a plus or minus in front of it, just the positive, because it says x is greater or equal to 0, is my inverse function, and I'm going to write it in inverse function notation. And then another power function, this time it's x to the third power. So we don't have to worry about defining positive or negative because it's an odd root and an odd exponent. So we are going to start by switching x and y. Isolate the y so that it's in function notation. X minus 1 divided by 2 equals y to the third. Cube root it. There's never a plus or minus in front of an odd root. If it's positive, then we're taking the positive root. That's it. And we're going to write this final answer in function notation. So it will be the third root of x minus 1 over 2. And if you want to simplify it one step further to get the root out of the denominator, you can. You may or may not have practiced doing that, so I can leave the answer like this for now. And there's the inverse function of 2x to the third plus 1. And that is all.